Hello students, this is Mr. Bornheimer, and today I'm going to come to you and talk to you about work. And it's not necessarily going to come to you and I'm not coming to talk to you about my job. I am coming to talk to you about work, what we recall, if you recall what we've been talking about in class, or how we view work from a physics standpoint. So today we're going to be talking about, literally talking about work. Okay, what is this work? Okay, in class, we introduced this idea that work is something that has to be, well, that it can be described mathematically. And we've come up with a simple equation for this. So we've said that work, which is a vector quantity, direction is important, is equal to force times a change in distance or displacement. Okay, and this change in distance is also directionally important. As a matter of fact, the force and the distance, or the displacement, have to be in the same direction. So we've kind of talked about this a little bit, and I kind of want to do one example problem just to get our feet wet so that we can understand what this work is. Okay, so imagine for a moment that we're a person, okay, and this person is going to step up onto a staircase. Okay, this person has a mass of 70 kilograms, and they are going to lift their entire mass straight up over the course of a staircase. But we'll say that this staircase is, or let's say they're going to jump up, or they're going to lift themselves up half a meter. Okay, so 0.50 meters. And we want to know what kind of work they're doing. Okay, now we're going to say that they're going to move up or accelerate opposite gravity. Now that's not necessarily always true. That would actually be, or we could say that they're going to step up with an acceleration of 2 meters per second or squared, or 1 meter per second squared. But really what we're going to do is we're going to say they have to lift themselves up past gravity. Okay, so they're basically going to do, they're going to apply a force that overcomes gravity. So we're going to say that the amount of force that they're exerting is just slightly more than what it would take for gravity to hold them down. Okay, so to figure this out, okay, we say that gravity is accelerating a person or holding a person downwards with an acceleration of negative 9.81 meters per second squared. And for a person that has a mass of 70 kilograms, okay, this would basically work out to a force in newtons that is equal to 9.81 times 70. So if you get out your handy dandy calculating device, we could say that 9.81, and it would be negative, times 70 is 686.7. We will round to 687. Okay, and I'm not so worried about significant figures in this problem. So 687 newtons. Okay, and this would be a negative 687 newtons. Well, if we were looking at a free body diagram of the person here, okay, and I was going to go ahead and draw the free body diagram, we'll say that the blue dot is that person, then I would say that they're being held down with a force of negative 686, or excuse me, 87 newtons. Now, because they're standing on the ground, okay, there's a normal force that's acting upwards, and that normal force is a positive 687 newtons. And when the person steps off the step, they're exerting a force of 687 newtons downward because of gravity. And as a result, okay, the ground is pushing back up with 687 newtons. So we could say effectively that if a person were to step lightly and not stomp, that in essence the force that's being applied to lift that person up the set of stairs is equal and opposite to their weight. So, because they're really only lifting their weight. So in our problem here, we could say, in essence, that the force being applied by a person is a positive 687 newtons. Okay? So what the question that I pose is, what work is the person doing to lift themselves up the stairs? And in order to do that, we need to start with our original equation. So we're going to say work is equal to F delta D. And these are all vector quantities. Direction is very important here. Because we're looking at work lifting a person up, opposite gravity, we're going in the positive direction. So whatever energy is used is going to be positive energy. The work is being done in the positive direction. So we say, and that's what we should expect in our answer. Okay, so 687 newtons times, and if you recall from the toolkit here that we're lifting 0.5 meters. Okay, so times 0.5 meters. And I'm going to go ahead and put this all in parentheses, like so. So this now becomes a very, very simple problem. And what we see here is we're going to take our 687 and we're going to multiply it by 0.5, or basically take 1/2 of it, and we get 343.5, or approximately 344. And this would be Newton meters, or a Newton meter, as we've talked about in class, is 344 joules. Okay, so in order to lift themselves up the staircase 1/2 meter, okay, fighting against their own weight, or lifting their weight, doing work on their body, a person would exert 344 joules of energy just to lift their body, to do work on their body, lifting them upward. Okay, so this is how we apply work. Now, we could also do an example of work in a negative direction. Okay, so for instance, let's take for this tennis ball. And let's say that this tennis ball is going to drop 2 meters, all right, from some height and hit the ground. Okay, so we know the tennis ball. Okay, and the tennis ball is approximately, let's see, I have some masses here, so let's get a good approximate weight for it. The tennis ball is approximately 0.1 kilograms. Okay, so really the weight's about equivalent. So we're going to go ahead and draw a tennis ball right here, and we're going to say that that tennis ball is going to fall to earth. Okay, so it's going to accelerate in the downward direction to earth. Now, there is going to be some set distance that the ball falls. Okay, so delta D. And we know that because the ball has mass, that some force is going to be applied because you have acceleration, okay, and you have mass. So what we can assume here is that there is going to be a force applied on this tennis ball. It's going to fall a certain distance, and because a force is being exerted over a distance, work must be done on the tennis ball. Okay, and that work is going to be done by Earth, okay, or, you know, this relationship between these two massive objects, Earth and the tennis ball, and that force is gravity. Okay, so we can go ahead and calculate this. So we know the mass, or we have identified the mass of this tennis ball as being 0.10 kilograms. The acceleration of this object is going to be at gravity, and because it's in the downward direction, we can call that a negative 9.8, okay, meters per second squared. And the distance I've already identified, or the change in distance, is going to be basically 2 meters, okay? So, but we have to look at this as distance final minus distance initial, because it is a change in distance. The distance initial is 2 meters. The distance final, okay, is 0 meters. So really, a change in distance is going to be 0 minus 2 meters. So you really end up with a change in distance of negative 2 meters. Okay? So this is what we're looking at, is how much work is being done. Okay, so we have all of this, we're working with it, and we can plug it into our equation for work. Work equals force times delta D. Okay. Interestingly enough, because we aren't given force, we can substitute in Newton's second law, which states that you have mass times acceleration, and then we just kind of throw delta D in there. So we have this equation for work, and it's all legit. And now we can plug in our values. The mass, 0.1 kilograms. The acceleration, negative 9.8 meters per second squared. And the change in distance, a negative 2 meters. Okay. And when you calculate all of this out using your handy dandy calculating device, okay, let's go ahead and do it. 0.1 times 9.8 times 2, it gives me 1.96 joules of energy. And that is going to be positive because you have a negative here and a negative here, and they will cancel each other out. Okay, so really the work, even in this situation, because it's going downward, is a positive 1.96 joules because of the way we've defined the system. Okay, that's the way it is. And if we were to have defined the system a little differently, for instance, if I were to have said that maybe, let me go ahead and grab a different pen color here. If I were to say this was the origin and this was a negative 2 meters, okay, well, frankly, it would have ended up the exact same way. We still would have ended up with a delta D of negative 2 meters. The acceleration due to gravity is negative 9.8 meters per second squared. So what we see here is that work most of the time will be positive, and it's going to be representing the amount of energy used to move an object. Okay, so this is work, and this is simple work. But what would happen if we were to apply a force at an angle? Okay, so let's go ahead and look at a scenario. Say we have a couch. Okay, so I'm going to go ahead and draw a couch here. Okay, so here's my couch, and I have a person standing here, and they're going to be pushing down on the couch. Okay, and they're trying to move the couch in this direction across the ground. Okay, well, a couple things here. First of all, we're going to zoom in. The angle with which they're exerting a force is going to be 45 degrees. Okay, so they're exerting an angle at 45 degrees. And they're really exerting a force kind of in this direction here. Okay, so this is the direction of the force that's being exerted. So this is what we have going on. We also need to specify some distance that the couch is going to travel. Okay, so the distance that the couch is going to travel in this particular scenario is going to be 3 meters. So we're going to say that the couch goes a total distance of 3 meters. All right, now if you recall, and if we were to look at this couch from a, we could say it could be from a free body diagram perspective. Okay, if this represented our couch, you'd have the force of gravity acting downward. You have the normal force acting upward. But now, when looking at this, we could also say, well, we're also applying a force at 45 degrees in this direction. And we will assume no friction. If there was friction, there'd be a tiny little bit of resistance in this direction, but we're going to assume that that friction doesn't exist. We're going to assume that we're moving the couch on a frictionless surface. We know that not to be true, but it'll make our calculation a little bit easier as we explore this idea. Well, in some ways, we can break this force applied down. Okay, so if I zoom in here, this force applied really has components, right? There's part of this force is acting in this direction, and part of this force is acting in this direction. Now, anything that's acting downward, so downward, is going to be counteracted by the normal force. So in some ways, there's going to be a force that kind of counteracts the purple force. Okay, and then they're going to balance each other out. So when it's all said and done, okay, and I'll just highlight. I'm going to highlight all the forces that basically cancel each other out. Okay, those all cancel out. And what happens is, because we split that applied force into components, really it can be represented by its components. So the only thing that is left unbalanced is this blue vector here. And that blue vector is going to be our representation of the force that's actually going to move the couch. Okay, so we can actually, there's actually an equation for this. And if you were to look at the trig, that equation works out to being that the work is going to be equal to the force, okay, times the distance, times the cosine of the angle of elevation, okay, or basically the angle above or below the horizontal that is effectively acting on whatever object we're trying to move, okay. So in our situation here, our angle is 45 degrees, and that's the angle that we're actually going to use. So everything else really isn't too bad. We just need to know the force applied, we need to know the angle, and we need to know the distance. And again, we can just kind of plug it all in and go with it. All right, so using this equation, let's say that the force applied was 100 newtons. I already specified the distance that the couch travels as 3 meters. And we're going to use the cosine, that's a funky S, the cosine of 45 degrees. Okay? So we can go ahead and multiply all this out. So you want to take out your handy dandy calculating device. And at this time, you really should have this out to try this. If you, like me right now, you do not have a graphing calculator, you're going to want to do the cosine of the angle first. And it's important that you recognize that this angle needs to be in degrees. Okay, so on your calculator, make sure your calculator is set in degrees, not radians. Okay, so we're going to go ahead and do this. So I'm going to take 45, the cosine of it. Okay, and then I'm going to multiply by 3, and then I'm going to multiply by 100. And I end up with the amount of work that is done to move the couch across the floor. And that amount of work is 212 newtons, or roughly 200 newtons. Okay, so this is what is done, okay, if you're working with something that has to deal with an angle. And I wanted to kind of expose you to it because we don't necessarily want to lose those trig skills that we used in projectile motion or some of the other component type problems that we talked about first semester. We really want to make sure that we stay up on those a little bit. So this is a great example of that. Okay. The last thing I want to talk about today, okay, is basically different types of graphs. Okay. And so in order to do that, I'm going to go ahead and take out a new sheet here. And I want to talk about graphs, okay? Basically, force displacement graphs. And I'm going to go ahead. Okay, so in looking at our force displacement graph, what we can see here is that, let's say that there's a constant force that's applied on an object, and as we apply that object or that force, it's moving an object a set distance. Okay, so we're just going to say that this is what we're looking at right now. Okay, this represents first of all, a constant force. And that constant force allowed there to be, okay, basically an increase in the distance. So it moved some distance. Okay, now, if we wanted to know the work done by looking at a force displacement graph, okay, so force in newtons, displacement in meters, we would we could do a couple of different things, okay? There are really two things that we've explored in this class that we can do with a graph. We can either A, we can find slope, or B, we can find the area under the curve. For those of you that are in calculus, basically we can either take the derivative, all right, so dx over dy, you know, kind of thing, we can take a derivative, or area under the curve, we can find the integral. Okay, so these are really our two options. And so what we're going to do is we're going to look at the graph and we're going to say, okay, what would each one of these look like, and then kind of decide which one relates to work. So if we took the slope, slope is a change in y over a change in x, and we're just going to look at this in terms of units, okay, or the variable. So if I go back to my graph, y is force, and delta d is, or y is my force, and x is my delta d, or my displacement. So if work was slope, then it would look something like this, basically force over distance. Okay, but from what you know about the equation for work, that's not it. So really, this is probably not the direction we want to go. Okay, now looking at an area under a curve, okay, let's go back to our graph and say, well, area under the curve would be equal to like all of this. Okay, well, and that's like a rectangle. Rectangles, to find the area of a rectangle, you really just need length times width. So if I wanted to find the area of this rectangle, or the area under the curve, I would just have to multiply its length times its width. Well, its length, okay, its length is force. So the area under the curve, or the area of the rectangle, is going to be equal to force, the length, and the width is delta d, so F delta d. Well, this definitely looks familiar. As a matter of fact, it certainly looks a lot like, if I scroll all the way back, this equation for work. This equation right here, okay? So what we see is that if we have a force displacement graph right here, the area under the curve is actually work. So if you have force and displacement, and you take the integral, or you find the area under the curve, you can actually find the work. So let's plug some values in here and see how this would look. Let's say that the force being exerted was 10 newtons. Okay, so, and the distance that the object went was 5 meters. Okay, this would be 2.5 meters. This here would be 5 newtons. Okay, so if I wanted to find the work that was done based on this graph, I could say, well, it was a force of 10 newtons over 5 meters. Okay, so the area under the curve, or the rectangle, would be 10 newtons times 5 meters. Okay, and what we end up with is force times distance equals work. The force, 10 newtons, times the distance, 5 meters, gives me 50 newton meters or joules. So that would be the work done. Not every graph is going to be beautiful like that. Oh, looks like it failed on me there. Okay, so here we go. And that's not quite what I was going for. Okay, so here we are. And, all right, not every graph is actually square like that. So if we wanted to find the area under the curve of, let's say, a force that's changing over time. So you might start off by pushing really hard, but then you get tired, and so the force kind of declines. Okay, so let's take a look at a graph that would look like that. Okay, a changing force. So here is our force displacement graph. Okay, and we start by providing a really hefty force, and we're pushing it a set distance and distance and distance, and as we get closer to our destination, it becomes less and less and less and less, and finally, okay, we've run out of effort, and now we're done. Okay, well, just because it's a different shape, okay, just because the force was changing, does not mean that we can no longer find the work that was done. Okay, it just means that we're going to have to use a different equation. We can no longer do length times width, but we can still find the work that's done. Work is still force times displacement. However, if the force is constantly changing, okay, then what we need to do is we need to look at that. And in a case like that, really we can only find that graphically if it's in some simple geometric shape, like this instance is a triangle. So here we have a triangle. The area under the curve of a triangle, well, that's pretty easy to find. The area of a triangle is 1/2 the base times the height. So really, if I wanted to find the area under the curve of this particular force displacement graph, I could say it's 1/2 the base, which is delta D, times the height, which is force. So if I knew how far it went, and I knew basically the starting force, okay, here, then I could find the area under the curve. Okay, so let's say that we're looking at the same situation with a starting force of 10 newtons, okay? But in this particular situation, I had to decrease the force over time, and as a result, I still pushed the couch 5 meters, but I didn't use a constant force. It was a changing force, okay? So again, I'm gonna kind of star this idea. So I have 1/2 5 meters times a force of 10 newtons, and this ends up being 25 joules of energy. Okay, so notice I applied the same initial force, it went the same distance, but because I decreased the force over time, okay, I did not end up with the exact same, okay, work that was done in this particular situation. I applied a constant force here. All right, so graphs can tell us a lot about the type of force, whether it's changing or constant, that's being applied when doing work in a situation. And the area under the curve is work here. Okay. Well, this ends the video on work, and hopefully you took some things away from this. There is some problems in your homework that deal with graphs. There's some problems in your homework that are going to deal with work, and I think there's very few, if any, problems that deal with angles, okay? But make sure that if you have any questions, you let me know by emailing me or contacting me at bclassroom.com. Thanks for watching.